Welcome back to Tronics Energy. So, in the past few videos episodes, we have been making an 8x1 logic unit, and we finished it up in our last season, where we had the final input as not B, given the code 111. Yes, that was the last input in our 8x1 multiplexer. But I said these are 74153 IC. It has two 4x1 multiplexers which are connected at the select only. So we had to connect them using their enable pins to make it to be an 8x1, a single 8x1 multiplexer. So for the 8x1 multiplexer, it could handle more than four inputs. So we kept the first four inputs in our first multiplexer A to D, which were AND, OR, NAND, and NOR. Then the final multiplexer, the other multiplexer, we kept XOR, XNOR, not A and not B. So those are all the inputs of the 8x1 multiplexer, and those are the logic operations which it will be doing for A and B. So the inputs are only two, they are A and B. Those are the inputs. So these are the logic gates, and we say that this episode we are going to run through all of them to make sure that the multiplexer is functioning as we intended in the first place. So I'll turn this off. Yes. Now we are going to start, and our first operation is AND operation. So it's going to be A and B. A and B. If you can remember the AND operation, both inputs have to be on in order to give an output. So it's at NAND operation right now because its code is 000, and because that 000 is at the select, meaning that the multiplexer is functioning AND operation only. So the LED is off since both inputs are off. So when we turn on B, the output should still remain off. So let's turn on B. The output is still off. Then let's turn on A and turn off B. That's the next configuration, 1 0. So this is 0 1. Then let's do 1 0, like that. 1 0, and the LED is still off. That's how it should be. Then when we turn on both inputs, the output should be 1. So let's turn on B, and when you turn on B, the output is on. So that's AND operation. And the select, we put 000. So 000 to our circuit, it knows that is AND operation. So that's the code we have given, and that's how it functions. So the AND operation is functioning properly. Let's go next to the OR operation. So let's turn off all these inputs. And the OR operation, the code is 001. So we place 001 in our select line. So 00, then this is on, like that. So 001. So that's the now the multiplexer is functioning under OR operation only, because that's the code for OR specifically. So for OR operation, if you can remember, either of the inputs should be on for it to give an output. Now, because both inputs are off, it's going to give a 0 output. Because both inputs are off, A and B are off, it's going to give a 0 output. But if either of the input is on, or both of them are on, it's going to give a 1 output. So let's start with B. Let's turn it on. Then there's an output. Okay, let's go with A. It's giving an output. Then when both inputs are on, it should also give an output. When both inputs are on, it should give an output. So that's OR operation, and the code for OR operation is 001. That's the code for OR operation. So it's functioning properly. Let's go next. I'm going to slide this so that we can see the table, like that. Now next we are going to a NAND gate. So let's turn off these inputs, turn them off. So for a NAND gate, check our code chart. Our code chart says that the NAND gate has the code 010. So this middle LED is the one that should be on, so it will be 010. So we turn off this other one, then we turn on the middle one. So 010 is the code for NAND operation. So let's go for NAND operation. NAND operation is just basically the opposite of AND operation. It's just the inversion of AND operation. So when there's 00, you get a 1. When there's 01, you get a 1. When there's 10, you get a 1. But when both inputs are on, you get a 0. So let's check. Both inputs are off. Yes. So we get both inputs are off. So we get a 1 output like that. So let's go next. When B is on, we get a 1 output still. So let's turn on B. We still get a 1 output. When A is on, we get a 1 output. So let's turn on A. We still get a 1 output. Then when both inputs are on, we should get a 0 output. So let's turn on B. When both inputs are on, we get a 0 output. So basically it's the opposite of AND, because AND, when both inputs are on, is when you'll get an output. But for an AND, when both inputs are on, you get a 0 output. So the NAND operation is working properly, and the code for the NAND operation is 010. So that's fine. Then we go next to our D3. D3 is a NOR operation, and for the NOR operation the code is that. So let's slide this truth table so that you can see. So NOR operation. So let's turn off these inputs so that we can start from the start. Yes. So NOR operation, the code is 011. So 011. So the first LED is the one that is off, the others are on. 011. And the LED immediately is on. So let's check the truth table. So NOR operation is basically the opposite of the OR operation. It's the inversion of OR operation. Since when both inputs are off, you get a 1 output. So that's the place you're going to get a 1 output only. The others you're going to get a 0 output. So when both inputs are off, you get a 1 output. So that's why you can see both inputs are off. We have gotten a 1 output. So if either of the inputs is 1, or both of them are 1, you'll get a 0 output. If you can remember, for the OR, if either of the inputs were 1, you'll get a 1 output. But for the NOR, because it's an inversion of an OR gate, when either of the inputs is 1, you'll get a 0 output. So let's check. So both inputs are off, you get a 1 output. So that's fine. So let's turn on B and check. We have gotten a 0 output because one of the inputs is off, is on. So let's turn on A and check. A, it's off, the output is off. Why? Because one of the input is on. Let's turn both of the inputs on. A and B are on, so we get a 0 output because either of the inputs is on. Because we said for the NOR gate, if either of the inputs is on, we get a 0 output. But when both inputs are off, we get a 1 output. When both inputs are off, we get a 1 output, and that's the NOR operation. So for the NOR operation, the code is 011 at the select line. So let's go next. Now we are entering the K data line, and we start with the K0 having the XOR operation. So I'm going to slide this. Like that so that we can see the exclusive OR operation. That's what we have next. So for the exclusive OR, the code is 100. 100 is the code for the exclusive OR. So we are going to place 100 in our select line. So we turn off this and we place 100. So that's 100. So the multiplexer now is functioning under the exclusive OR operation only, exclusive OR. So let's check the truth table. So for the exclusive OR, if the inputs are alike, basically if the inputs are alike, we get a 0 output. But if the inputs are different, they are different, then we get a 1 output. So if the inputs are 0 0, you get a 0. Inputs are 1 1, you get a 0. But when the inputs are 0 1, you get a 1. 1 0, you get a 1. So let's check. Because the inputs are 0 0, we have gotten a 0. If either of the let's do this one for, let's do this second configuration. B is on, so we expect to get a 1 output. Because they are not alike, so we get a 1 output. One of them is 0, the other one is 1. Let's do this one for A. A is on, B is off. So A is on, B is off. Because one of them is on, the other one is off, we get a 1 output. When both inputs are on, we get a 0 output. So let's turn on B. When both inputs are on, we get a 0 output. So that's basically how the exclusive OR operation or exclusive OR gate function. So when both inputs are alike, we get a 0 output. When both inputs are, if the inputs are not alike, we get a 1 output. Let's go next to our exclusive NOR operation. Exclusive NOR. So let's turn off these inputs like that and select yes. Let's turn to our exclusive NOR. So for our exclusive NOR, in our sheet here, we gave it the code 101. 101 is the exclusive NOR. So we are going to place 101 in our select. So the middle one is the one that is not on. So 101 is the code for exclusive NOR, this exclusive NOR. And the operation for the exclusive NOR is just basically the inversion of an exclusive OR. Yeah, you can see if when both inputs are alike, we get a 1 output. But if they are not alike, we get a 0 output. You can just check the output are just the opposite of each other. When both inputs are alike, we get a 1 output. But if the both inputs are not alike, we get a 0 output. So let's check. Both inputs are off, we have gotten a 1 output. So that's true. If either of the input is on and the other one is 0, then we get a 0 output. So let's turn on B. Let's turn on B only. Yeah, when we turn on B only, 0 1 0 1, we get a 0 in the output. You can see here. Let's go with A 1 0. So we turn on A like that. 1 0. We get a 0 because they are not alike. But when you turn on both inputs on, we expect to get an output. So let's check. We turn on both of them, then we have gotten an output the same as when they were 0 0. We got an output. So because they are alike again, 1 1, we have gotten an output. So if we turn them back on to 0 0, we should get an output. So that's the exclusive NOR operation. And the code for the exclusive NOR operation 101 101 in our select line. Yes, and it's continuing on well. Now let me slide this that we can see the last two operations of our 8x1 multiplexer, 8x1 logic unit. Yes, so next up we have NOT A. NOT A operation, we gave it the code 110 in our select line. So we place this code in our select line 110. So just turn off this, then we place 110 in our select line, and it's going to do NOT A operation. And as we said, because the NOT gate has only one input, and has only one input, then the configuration will only be two. It will be either on or off, nothing more than that. It's not like a NOR gate which has two inputs. because that's 2 inputs, it should have 4 different configurations. But because the NOT gate has only 1 input, it's only going to have 2 possible ways, either on or off. Okay, yes. So for the NOT gate, NOT A, it's going to check the inversion of A only, and we said that this first LED or this first section of the input is A, and the other one is going to be B. So we are going to check this one. So the code is not A, and this is the one that's A. And for the inversion, for the NOT gate, it's just basically the inversion of the input. If the input was 0, we get a 1. If the input was 1, we get a 0. So since A is now currently 0, we have gotten a 1. Yes. And when you turn on A, we expect to get a 0 in the output. So if we turn on A, we have gotten a 0 in the output. Yes, if we turn off A, we expect to get a 1 in the output. So when you turn off, you get our 1 in the output. And it's not affected by B because it's only doing, you can see, not affected by B because we are only dealing with A only. Only dealing with A. So for the B, it has its own code in our select. Okay. So let's do that again. So when A is off, we get a 1. When A is on, you get a 0 because we are just inverting the state of A. We are just inverting the state of A. So like that. So we have given that the code 110 in our select line. So let's continue. We have our last input in our 8x1 multiplexer, which is NOT B, and the code is 111. This is binary for 7. Yes, this is a binary for 7. And why we are calling it an 8x1, because we are starting to count from 0. If we started from 1, then it would be 7x1, but because we are starting from 0, then it's going to be an 8, because when you count these 1, 2, 3, 4, 5, 6, 7, 8, yeah, 8. But this is a binary for 7. So this is the last input in our 8x1 multiplexer. And so let's place this code in our select line. Let's place this code in our select line. And the operation is not B. It's just basically exactly the same for A, only that this time we are concentrating with B, the input B, this other one. So it's still going to do the same thing that the A was doing. When B is off, we get a 1 output, and when B is on, we get a 0 output. So let's see. So B is off currently, so that's why the output is 1. And when we turn on B, we expect to get a 0 output. So let's turn on B. We have gotten a 0 output. Okay, so let's turn it. When we turn it off, we get a 1 output. So let's turn it off. Then we get a 1 output. And it's not affected by A. It's not affected by A. Since we are concentrating with only B, you can see nothing is really happening to the output. Even if I turn this A on and off, nothing is happening. But when I turn on B, it's off, because when B is 1, we get a 0 output, and when B is off, we get a 1 output. So that's the operation of a NOT B, and that was our last input in our 8x1 logic unit. So I hope you have understood what we meant by the logic unit. It's just a system. It's a system that we have made to be doing logic operations only, and it has done all the logic operations possible. We have AND, we have OR, we have NAND, NOR, XOR, XNOR, NOT A, and NOT B. So that's basically what the logic unit was to do, and it has functioned very well. If you have been following along, you can make this circuit at home using various ICs that I'm using here. Like for example, we start off with this 74HC08 has I think 4 AND gates in it. Next up we have a 7432 it's an OR gate having 4 inputs, the same as for the AND gate. Next up here, you can see this little guy is quite full. This is a NOT gate, and I'm using I've used basically all of the possible, all of the NOT gates in this IC. It's an X inverter, meaning that it has 6 NOT gates in it, and I've used all of them. It's a 74 HC, let me see, 04. Yeah, it's 04, 74 HC 04. Then finally here we have 7486. It's an XOR gate, has 4 XOR gates, and one of them I've used as an XOR. The other one I've connected to a NOT gate to make an XNOR because I don't have an XNOR. Yes. Then finally here we have our 74153 IC. It has 2 4x1 multiplexers looking like this. So we connected those 2 multiplexers together via the enable pins to make it an 8x1, able to operate 8 different logic operation using only one select line, yes, and only one output. So yes, so I hope you have understood the construction of the 8x1 logic unit. Next time we are going to do an arithmetic unit. The arithmetic only will only have maybe just adders and subtractors only. I don't know if I'm going to add maybe a multiple, but a multiplier is quite a big circuit. I don't think I'm going to add it, but basically it will have the adders and subtractors, just 2 of them, adders and subtractors. Then from there we are going to do add both the adders and subtractors and the logic unit to make the arithmetic and logic unit. So basically I'm going to remove NOT A and NOT B. So this place we are going to place the arithmetic section. We are going to place maybe add and subtract here. We're going to remove these 2 little guys. Yes, so that the multiplexer can handle, so that the multiplexer can have space for the arithmetic operation. So thank you very much guys for watching. Please subscribe to Tronics Energy and hope to see you next time. Goodbye.